Here's a slow motion video of a cylinder placed in Cal Poly's low speed wind tunnel with a smoke stream flowing around it. It can be seen that the flow separates as it passes over the cylinder, creating turbulent airflow behind it. The flow also visibly oscillates up and down, changing where on the cylinder the separation point is. Understanding this concept, called vortex shedding, is key to understanding drag forces on objects.
The pressure coefficients recorded on the cylinder when running the wind tunnel at 350 RPM shows that the flow matches the theoretical pressure distribution fairly closely in the center of the cylinder, but detaches about halfway around it. This is seen between the angles of 100-ish and 250-ish degrees, where the pressure distribution basically becomes flat instead of following the sine curve. At 600 RPM, the pressure distribution is fairly similar, in addition to the detachment point being in roughly the same place. However, the pressure coefficient on the rear faces of the cylinder, where the line is flat, is a little bit smaller, closer to 0. This is likely because the pressure coefficient is defined relative to the stagnation pressure, which will be higher when the wind is going faster, whereas the pressure behind the cylinder should be roughly the same.
The potential flow equation is derived from starting with a couple of assumptions, including incompressible, irrotational, and viscid flow, then using the basic laws of fluid mechanics, including the conservation of mass momentum, satisfying the Laplace equation, finding the component velocities using Bernoulli's equation, and then solving for the coefficient of pressure. In many cases, the potential flow equation is helpful in understanding the flow around an object or predicting it. In our case, the potential flow equation is useful in understanding the flow in front of the cylinder, but not behind the cylinder because of viscous and rotational effects.
The pressure coefficients gathered when running the wind tunnel at 0 RPM have very little meaning to them. Since the pressure coefficient is defined by the difference between the static and dynamic pressure, which are both roughly the same when there's no wind speed, all of these numbers carry basically 0 information. This excuses the ones which are well above 1, as again, they are meaningless. Looking at the standard deviations across all of the pressure ports, there is a fairly noticeable dip right around the leading edge. This is likely because at the front half of the cylinder the flow is fairly laminar, whereas once it detaches there's much more turbulence going on, leading to a much higher standard deviation across the ports as the vortex shifts back and forth.
Comparing pressure coefficients at different speeds, it can be seen that the pressure coefficient in the region behind the cylinder had a lower magnitude at a higher fan speed, and thus a higher Reynolds number. This indicates that the object will have lower drag coefficients at higher Reynolds numbers. This conclusion matches the expected behavior indicated by other sources.
The Strouhal number uses the frequency of vortex shedding, characteristic length, and free stream velocity. It characterizes the pattern of vortices forming on the cylinder and releasing into turbulent flow. We only took the video for the run with the wind tunnel fan at 600 RPM, so the calculated Strouhal number for this situation is 0.0843. This is smaller than expected, according to an approximation of the Strouhal number that is 0.198 times the quantity of 1 minus 19.7 over Reynolds number. However, this is only an approximation, and there's a large amount of error just from the crude calculation of the vortex shedding frequency from timing a slow motion video.
The coefficient of drag on the cylinder is shown here for different RPMs. For the 0 RPM setting, the coefficient of drag was roughly 0. For the 350 RPM setting, the coefficient of drag was approximately 1.35, and in the 600 RPM setting, the coefficient of drag was lower than the 350 RPM, and it was 1.2 approximately. This plot shows the coefficient of drag against Reynolds number. Note that we only have 3 data points, one being at 0, so this plot may not be representative of the complete trend. Looking at the coefficient of drag plotted against Reynolds number for a cylinder, we first note that the Reynolds number of 0 is not included, so a situation with 0 velocity is not included. Thus, our plot looks a little bit different because we start at 0. Following, we see that as Reynolds number increases, coefficient of drag actually decreases, which follows our trends for our last 2 data points.
Generally, more roughness will cause more separation because rough surfaces will interrupt the laminar flow, causing separation earlier along the object. However, there are instances where roughness can create a thin layer of turbulent flow that can actually cause the laminar flow around it to flow further around the object than a smoother surface would accomplish. With less separation, there is also less pressure drag. This is taken advantage of with golf ball design, where the dimples cause this very phenomenon to allow them to go further with less drag.
Looking solely at the recorded pressure distribution compared with the theoretical pressure distribution, one may notice that it is slightly shifted to the right, indicating a little bit of downforce being generated from the cylinder. However, it is also entirely possible that this is because the pressure port at the leading edge was not actually facing directly into the free stream, and this is where the theoretical pressure distribution is based on.
From looking at the slow-mo video of flow going over the cylinder, you can see that the flow is actually three-dimensional, as a plume of smoke seems to travel span-wise here. The idealization of 2D flow helps with calculations, but is nearly impossible to recreate given the geometric or ambient irregularities in the wind tunnel.
Spheres and cylinders, while both having circular cross-sections, create many differences in their flow. Cylinders are ideally treated without boundary conditions at their ends, in our case where they meet the sides of the wind tunnel. This means that their flow can be simplified to a two-dimensional problem because of their consistent cross-sections span-wise. This 2D simplification can be seen in the left figure. However, a sphere must always be treated as a three-dimensional problem because of the inconsistent cross-section that causes the three-dimensional flow, even in ideal conditions, such as the figure on the right. Roughness generally has the same effect independent of whether the object is a sphere or a cylinder. Either way, the flow will separate and transition from laminar to turbulent flow earlier. Drag is significantly affected by the difference between spheres and cylinders, but the relationship depends on Reynolds number. The figure shows coefficients of drag versus Reynolds number plots for both spheres and cylinders. At low Reynolds numbers, the sphere has higher drag, but as the Reynolds numbers increase, cylinder drag becomes much greater than sphere drag. Cylinders have an entire line of stagnation points, and 2D cross-sectional flow ideally occurs in each plane, but spheres have a single stagnation point and 3D flow goes all the way around the sphere, causing less drag at higher velocities.
So where else do we see boundary layer tripping? A natural example is trees, which have rough bark that disturb the boundary layer. A human-made example is smokestacks, which are sometimes fitted with helical strakes that disturb the boundary layer around them.